Welcome to a unique journey into the very fabric of existence. As the day gently recedes, we invite you to settle into a space of calm contemplation, letting your thoughts drift away from the day's demands. Tonight, we embark on an exploration of the universe's most fundamental building blocks, atoms. We will uncover approximately 100 fascinating facts that reveal the intricate patterns, subtle wisdom, and profound beauty within these minuscule marvels that compose everything around us and indeed within us. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge, flowing without demanding effort or attention. We will observe the intricate dance of subatomic particles, the subtle forces that bind them, and the quiet wisdom embedded in their omnipresence. Each fact is a small window into the vast and interconnected tapestry of matter, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. If you're finding peace in this journey, a like and subscribe helps us continue creating these restful explorations. And we're always curious. Share in the comments what city and time zone you're watching from. There's something special about knowing this experience is reaching people all over the world as they prepare for rest. Tonight, we begin our exploration at the very beginning, delving into the foundational nature of atoms. These tiny entities are the invisible threads that weave together the tapestry of our reality, and understanding their basic composition offers a profound sense of the universe's elegant design. Let us quietly observe the fundamental principles that govern these ubiquitous and essential particles, the ancient concept and modern definition. The idea of the atom as an indivisible unit of matter dates back to ancient Greece, where philosophers like Democritus, around 400 BCE, proposed that all matter was composed of tiny, uncuttable particles. He coined the term atomos, meaning uncuttable or indivisible. Current understanding suggests that while individual atoms can indeed be split, they remain the smallest unit of an element that retains its chemical identity. Scientists have observed that every element in the periodic table, from hydrogen to oganesson, is defined by its unique type of atom. This foundational concept underpins all of chemistry and physics, providing a framework for understanding how matter behaves and interacts. Research shows that atoms are truly the basic building blocks, combining in countless ways to form the molecules that make up everything from a single water droplet to a distant star. The journey of atomic theory from Fermi philosophy to sophisticated quantum mechanics reflects humanity's persistent quest to understand the universe at its most fundamental level. The vast emptiness within. Despite their role as the building blocks of all matter, atoms are, surprisingly, mostly empty space. If an atom were expanded to the size of a football stadium, current understanding suggests that its nucleus, containing almost all of its mass, would be no larger than a pea or a marble at the centre. The electrons, which define the atom's outer boundary, would be like tiny dust motes whirling far away in the stadium's upper reaches. This astonishing emptiness means that the solidity we perceive in everyday objects is largely an illusion, a result of the electromagnetic forces between the electrons of different atoms pushing against each other. Scientists have calculated that if all the empty space within the atoms of humanity were removed, the entire human population could fit into a sugar cube. This profound emptiness is a cornerstone of modern physics, challenging our intuitive sense of what solid truly means and inviting a deeper contemplation of the nature of reality. Protons, the identity makers. At the very heart of every atom lies the nucleus, and within that nucleus reside particles known as protons. Each proton carries a single positive electrical charge, which is a fundamental property of matter. The number of protons in an atom's nucleus is what defines its atomic number, and consequently its identity as a specific chemical element. For instance, an atom with 1 proton is always hydrogen, an atom with 6 protons is always carbon, and an atom with 8 protons is always oxygen. Research shows that changing the number of protons fundamentally changes the element itself, transforming it into something entirely different. The strong nuclear force, one of the 4 fundamental forces of nature, binds these positively charged protons together within the tiny nucleus, overcoming their natural electromagnetic repulsion. Scientists have observed that the proton's mass is significantly greater than that of an electron, contributing substantially to the atom's overall weight. Neutrons, the stabilizers. Also nestled within the atom's nucleus are neutrons, which, as their name suggests, carry no electrical charge. They are electrically neutral. While they don't determine an atom's identity in the way protons do, neutrons play a crucial role in stabilizing the nucleus. Without neutrons, the positively charged protons would repel each other so strongly that most nuclei would simply fly apart. Current understanding suggests that neutrons act as a kind of nuclear glue, adding to the strong nuclear force without adding to the electromagnetic repulsion. The number of neutrons in an atom can vary within the same element, leading to what are known as isotopes, which we will explore further. Scientists have observed that neutrons have a mass very slightly greater than that of protons, though for most practical purposes, their masses are considered nearly identical. The presence of neutrons allows for a wider array of stable atomic configurations, contributing to the diversity of elements found in the universe. Electrons, the energetic orbiters. Whirling around the dense atomic nucleus are electrons, tiny particles that carry a single negative electrical charge. These electrons are incredibly lightweight compared to protons and neutrons, with a mass approximately 1086 times smaller than a proton. Current understanding suggests that electrons do not orbit the nucleus in simple planetary paths, but rather occupy probabilistic orbitals or electron shells, representing regions where they are most likely to be found. The number of electrons in a neutral atom is equal to the number of protons, ensuring that the atom has no net electrical charge. Research shows that it is these outermost electrons known as valence electrons that are primarily involved in chemical bonding, determining how atoms interact with each other to form molecules. Their constant rapid motion and the electromagnetic force they exert create the effective size of an atom and dictate its chemical behavior. This dynamic dance of electrons is fundamental to all chemical reactions and the very existence of matter as we know it. The nucleus, the atom's dense heart. At the very core of every atom lies the nucleus, a remarkably dense and tiny region that contains nearly all of the atom's mass. Composed of protons and neutrons, which are collectively called nucleons, the nucleus is held together by the incredibly powerful strong nuclear force. Scientists have observed that despite its minuscule size, typically about 100,000 times smaller than the entire atom, the nucleus is a powerhouse of energy and interaction. The stability of the nucleus determines whether an atom is radioactive or stable, influencing its potential for nuclear reactions. Current theory suggests that the ratio of protons to neutrons within the nucleus is a critical factor in its stability. Too many or too few neutrons can lead to instability and radioactive decay. This compact, energetic core is where the atom's identity is forged and where immense forces are at play, quietly governing the fundamental properties of all matter. Atomic number, the unique identifier. The atomic number, denoted by the symbol Z, is arguably the most crucial identifier for any atom. It represents the exact number of protons found in the nucleus of an atom. This number is unique to each chemical element, meaning that every atom of a given element will always have the same atomic number. For example, all carbon atoms, without exception, possess 6 protons, giving carbon an atomic number of 6. Scientists have meticulously organized the periodic table of elements based on increasing atomic number, which reflects the fundamental order of matter. Research shows that if an atom gains or loses a proton, it fundamentally transforms into a different element altogether. This immutable characteristic defines an element's place in the universe and dictates its fundamental chemical properties, making the atomic number the true fingerprint of an atom's identity. Isotopes, variations on a theme. While the number of protons defines an element, the number of neutrons within an atom's nucleus can vary, leading to what are known as isotopes. Isotopes are atoms of the same element, meaning they have the same number of protons, but possess different numbers of neutrons, and therefore different atomic masses. For instance, carbon-12 has 6 protons and 6 neutrons, while carbon-14, a radioactive isotope used in carbon dating, has 6 protons and 8 neutrons. Scientists have observed that while isotopes of an element share nearly identical chemical properties due to having the same number of electrons, their physical properties, such as mass and nuclear stability, can differ significantly. Current understanding suggests that many elements in nature exist as a mixture of several stable isotopes. This variation allows for a broader spectrum of atomic forms within each element, adding nuance to the fundamental building blocks of the universe. Constant motion and energy. Even at absolute zero, the theoretical temperature at which all atomic motion ceases, atoms still possess quantum mechanical zero-point energy, indicating an inherent, irreducible vibration. However, at any temperature above absolute zero, the particles within an atom are in constant, vigorous motion. Electrons rapidly orbit the nucleus. Protons and neutrons vibrate within the nucleus, and the entire atom itself can move, rotate, and vibrate, especially when part of a molecule. Research shows that this ceaseless motion is directly related to temperature. Higher temperatures mean more energetic and rapid atomic movement. This intrinsic dynamism of atoms is what drives diffusion, heat transfer, and countless other physical processes. The universe, at its most fundamental level, is a place of constant, vibrant movement, a silent, intricate dance of particles that never truly rests. As we conclude this initial glimpse into the world of atoms, we have seen that these invisible foundations are far from simple. They are intricate systems of fundamental particles bound by powerful forces and characterized by both stability and ceaseless motion. From the ancient philosophical concept to the modern understanding of their internal structure, atoms reveal a universe built on elegant principles, each one a testament to the quiet order underlying all existence. Let these initial insights into their fundamental nature gently settle, preparing us for deeper explorations in the chapters to come. The ceaseless activity of these tiny components, this constant motion, is not a chaotic frenzy, but rather an intricate dance, governed by a profound and elegant rules. As we gently drift deeper into the atomic realm, we begin to appreciate the remarkable order underlying what might initially seem like pure randomness. Let us continue our serene journey, exploring the delicate mechanisms that give rise to the stability and diversity of all matter. Fact 6. Electrons reside in quantized energy levels. Imagine, if you will, a grand invisible staircase spiraling around the nucleus of an atom. The electron, those nimble negatively charged particles, do not simply roam freely or orbit at any arbitrary distance. Instead, they are confined to specific steps on this staircase known as energy levels or shells. Each step represents a precise, discrete amount of energy an electron can possess. An electron can be on the first step or the second or the third, but never ever floating somewhere between the steps. This fundamental principle, known as the quantization of energy, is one of the most astonishing discoveries of quantum mechanics. It means that the energy within an atom is not continuous but comes in distinct, indivisible packets. This concept brings a profound sense of stability to the atomic world. If electrons could lose energy gradually and continuously, they would eventually spiral inward and collapse into the nucleus, and all matter would cease to exist. But because they can only occupy these specific energy levels, they are held in a delicate, balanced state. Current understanding suggests that this quantization ensures the enduring structure of atoms, providing the very foundation upon which all chemical interactions are built. We find a quiet order here, a reassurance that even at the smallest scales, there are rules that maintain harmony. Fact 7. Electron transitions emit and absorb light. Now, picture an electron resting peacefully on one of its designated energy steps. It can, however, move to a higher step, but only if it gains a precise amount of energy. This energy often comes in the form of a tiny packet of light called a photon. When an atom absorbs a photon, one of its electrons makes a quantum leap to a higher, more energetic level, entering what we call an excited state. This absorption is incredibly specific. The photon's energy must exactly match the difference between the two energy levels for the electron to jump. Conversely, an electron in an excited state is eager to return to its more stable, lower energy levels. When it does so, it releases the excess energy it acquired, again in the form of a photon. The color of this emitted photon, whether it's red, blue, or ultraviolet, depends entirely on the energy difference between the steps the electron traversed. This beautiful dance of absorption and emission is the secret behind the vibrant colors we see in the world. From the warm glow of a campfire to the precise hues of a neon sign, scientists have observed these unique spectral fingerprints for every element, allowing us to identify the composition of distant stars simply by analyzing the light they emit. It is a testament to the elegance of atomic mechanics that the universe communicates its composition through these silent, shimmering messages of light. Fact 8. The electromagnetic force weaves the fabric of our reality. As we discuss the positive charge of protons and the negative charge of electrons, we touched upon a truly fundamental interaction, the electromagnetic force. This force is the invisible architect behind the world we perceive with our senses. It is the powerful attraction between oppositely charged particles, holding electrons in their quantized orbits around the positively charged nucleus. It is also the repulsion between like-charged particles, preventing electrons from piling on top of each other and keeping the protons in the nucleus from flying apart, though another force is even stronger there. At the atomic and molecular level, the electromagnetic force is incredibly potent, vastly outweighing the pull of gravity. It is this force that dictates how atoms bond together to form molecules, how these molecules interact to create liquids and solids, and why matter feels solid to our touch. The perceived solidity of a table, for instance, isn't because its atoms are physically touching, but because the electromagnetic forces between the electrons of your hand and the electrons of the table are repelling each other with immense strength. Research shows that this force is responsible for all chemical reactions, for the flow of electricity, and for the very existence of light itself. It is a pervasive, silent giant, constantly shaping and defining the intricate tapestry of our reality. Fact 9. The strong nuclear force, the universe's ultimate glue. Deep within the heart of every atom, nestled in the minuscule nucleus, resides a power so immense it defies easy comprehension. The strong nuclear force. We know that protons with their positive charges naturally repel each other due to the electromagnetic force. Without something to counteract this powerful repulsion, atomic nuclei, especially those with multiple protons, would simply explode. Here, the strong nuclear force steps in, acting as the ultimate nuclear glue. It is the strongest of the four fundamental forces in the universe, an unimaginably potent bond that holds protons and neutrons together within the nucleus. Its power, however, comes with a crucial limitation: its range. The strong nuclear force acts only over incredibly short distances, essentially within the confines of the nucleus itself. Beyond a tiny fraction of a nanometer, its influence rapidly diminishes, allowing the electromagnetic repulsion between protons to dominate. This delicate balance between the immense attractive power of the strong force and its limited reach is what dictates the stability of different atomic nuclei. Scientists have meticulously mapped its behavior, confirming its critical role in ensuring the existence of all the elements heavier than hydrogen. This silent, powerful guardian at the atom's core is a testament to the intricate balance that allows matter to endure and for the cosmos to unfold. Fact 10. The weak nuclear force, a subtle shaper of elements. While the strong nuclear force binds the nucleus together, and the electromagnetic force governs electron interactions and chemical bonding, there is another fundamental force quietly at work: the weak nuclear force. Though less intuitive in its daily manifestations, its influence is profoundly significant, particularly in the realm of elemental transformation. The weak force is responsible for certain types of radioactive decay, most notably beta decay. In this process, a neutron can transform into a proton, emitting an electron and an elusive particle called an antineutrino, or vice versa. This subtle transformation leads to a change in the atomic number of an atom, effectively converting one element into another. It is a slower, more deliberate process compared to the instantaneous interactions of the electromagnetic and strong forces. The weak force plays a crucial role in the evolution of stars, powering the fusion reactions that create the elements essential for life, and in the radioactive decay that heats Earth's core. Research shows that this force, though weaker than the strong and electromagnetic forces, is a vital player in the universe's ongoing narrative of creation and change, gently reshaping matter over vast stretches of time. It reminds us that even seemingly stable elements are part of a grand, slow dance of cosmic alchemy. Fact 11. Gravity's whispers at the atomic scale. Among the four fundamental forces, gravity is perhaps the most familiar, the force that keeps our feet on the ground, the moon in orbit, and galaxies bound together. Yet, when we descend to the atomic scale, gravity's majestic roar diminishes to an almost imperceptible whisper. The masses of protons, neutrons, and electrons are so incredibly tiny that their mutual gravitational attraction is astronomically small compared to the other forces at play within an atom. For instance, the electromagnetic attraction between a proton and an electron is about 10 to the 39 times stronger than their gravitational attraction. This means that while gravity shapes the cosmos on its grandest scales, it has virtually no discernible effect on the internal structure or interactions of individual atoms. The intricate dance of electrons and the steadfast embrace of the strong nuclear force utterly dominate the atomic realm, rendering gravity's influence negligible. This fascinating dichotomy reminds us of the scale-dependent nature of physical laws, where different forces take precedence depending on the vastness or minuteness of the canvas upon which they paint. It offers a peaceful reflection on how the universe organizes itself with such elegant, hierarchical precision. Fact 12. Every element holds a unique atomic fingerprint. As we journey further, we arrive at a foundational truth that brings order to the entire chemical universe. The number of protons in an atom's nucleus is its immutable identity. This specific count is known as the atomic number, represented by the letter Z. If an atom has one proton, it is, by definition, hydrogen. If it has 6 protons, it is carbon. 79 protons invariably mean it is gold. This unchanging principle is the ultimate identifier, the unique fingerprint of every element. No two elements share the same atomic number, ensuring that each has its own distinct set of chemical properties and behaviors. This unwavering characteristic is what allows scientists to classify and understand the vast diversity of matter around us. It is the bedrock upon which all chemical understanding is built. This immutable relationship between the number of protons and an element's identity has been confirmed through countless experiments and observations, forming the very foundation of modern chemistry. It offers a profound sense of order and predictability, a quiet reassurance that beneath the seeming complexity of the world, there lies a simple, elegant system of classification, inviting us to appreciate the distinct personality of each elemental building block. As we continue our gentle exploration, we find ourselves drifting deeper into the atomic realm, where the ceaseless activity of particles gives rise to all the forms and functions we observe. In this chapter, we marveled at the forces that govern these tiny worlds, from the electromagnetic dance of electrons to the mighty strong nuclear force. Now, let us turn our attention to how these individual atomic entities come together, weaving the very tapestry of our reality. Fact 10. Atoms form bond to achieve stability. Imagine, if you will, that each atom possesses a quiet desire for completeness, a gentle yearning for a balanced state where its outermost electron shell is either full or empty. This fundamental drive for stability is the primary architect of chemical bonding, the intricate process by which atoms join together to form molecules. We observe that atoms achieve this serene balance through various means. They might share electrons in a harmonious partnership known as covalent bonding, where electrons orbit 2 or more nuclei simultaneously, creating a strong, stable link. Or they might engage in a more direct exchange, where one atom gently gives up an electron to another, forming ionic bonds. In this dance, one atom becomes slightly positively charged and the other slightly negatively charged, and these opposite charges then draw them together with an elegant electromagnetic embrace. Current understanding suggests that nearly all the matter you can touch, see and feel, from the air you breathe to the very cells of your body, is held together by these invisible yet incredibly powerful atomic bonds. Scientists have observed that the strength and nature of these bonds dictate the properties of every substance, determining whether it is a hard diamond or a soft whisper of gas. This profound interconnectedness reminds us that even at the most fundamental level, cooperation and balance are the keys to creation. Lore. Fact 18. Molecules are atoms working together. When atoms form these stable bonds, they create new entities we call molecules. A molecule is simply a group of two or more atoms held together by chemical bonds, acting as a single, distinct unit. Consider the tranquil simplicity of a water molecule, H2O, where two hydrogen atoms graciously share electrons with a single oxygen atom. Or ponder the life-giving oxygen we inhale, O2, a molecule composed of just two oxygen atoms bound together in perfect harmony. These molecular structures are the true building blocks of the more complex world around us. Research shows that the specific arrangement and type of atoms within a molecule determine its unique characteristics and how it interacts with other molecules. It is the molecular architecture that gives water its liquid properties, allows sugar to dissolve, and enables proteins to fold into the intricate shapes necessary for life. We see that while individual atoms are fascinating, their true potential for complexity and diversity blossoms when they come together in these molecular partnerships, creating a universe of possibilities from a limited set of atomic components. Fact 19. The periodic table organizes all known elements. As we gather more facts about atoms, we inevitably encounter the periodic table of elements, a truly magnificent and elegant masterpiece of scientific organization. Imagine it as a grand cosmic map, charting every known type of atom in the universe. Each element, defined by its unique atomic number, the number of protons in its nucleus, occupies a specific place on this table. The elements are arranged not randomly, but by increasing atomic number, and also in rows and columns that reveal profound patterns in their chemical behavior. Current understanding suggests that this table is not merely a list, but a predictive tool. Elements in the same column, for instance, tend to share similar properties because their outermost electron shells are configured in comparable ways, leading to similar bonding tendencies. Scientists have observed that the periodic table allows us to anticipate how an element will behave, even before it has been fully studied, or, in some cases, even before it has been created in a laboratory. It is a testament to the underlying order and elegance of atomic design, a quiet reassurance that the universe, in its vastness, adheres to beautiful, discoverable rules. Fact 20. Isotopes offer unique insights and applications. We previously touched upon isotopes, those gentle variations of an element that possess the same number of protons but differ in their number of neutrons. While their chemical identity remains the same, their slightly different masses give them unique properties that we can harness for a multitude of purposes. Consider carbon-12, the stable form of carbon that makes up much of life, versus carbon-14, a radioactive isotope. This subtle difference allows us to precisely date ancient artifacts and fossils, peering back into the quiet echoes of time. Research shows that isotopes are invaluable tools in medicine, industry, and scientific research. For instance, specific isotopes of iodine can be used to treat thyroid conditions, while others are employed as tracers to illuminate processes within the human body without invasive procedures. We also find stable isotopes used in environmental science to track water sources or study climate change over millennia. The existence of isotopes reminds us that even within the seemingly fixed identity of an element, there lies a gentle spectrum of possibilities, each offering a unique lens through which to understand our world. Fact 21. Atomic mass is measured in atomic mass units, AMU. When we speak of the weight of an atom, we are typically referring to its atomic mass, a precise measurement of its heft. Because atoms are so incredibly tiny, using standard units like grams or kilograms would result in numbers so small they would be unwieldy. Instead, scientists developed a special unit, the atomic mass unit, or MU. One AMU is defined as approximately the mass of a single proton or neutron, which is roughly 1/12 the mass of a carbon-12 atom. Current understanding suggests that an element's atomic mass, as listed on the periodic table, is usually an average of the masses of all its naturally occurring isotopes, taking into account their relative abundances. For example, chlorine has two main isotopes, chlorine-35 and chlorine-37, and its average atomic mass reflects the weighted average of these two. Scientists have observed that this standardized unit allows for clear and consistent comparisons between the masses of different atoms, providing a fundamental basis for understanding chemical reactions and the composition of matter. It is a quiet acknowledgement of the intricate balance of nature, where even the smallest differences are carefully accounted for. Fact 22. Elements span a vast range of atomic numbers. From the simplest atom, hydrogen, with its solitary proton, atomic number 1, to the incredibly complex and fleeting super-heavy elements synthesized in laboratories like oganesson, atomic number 118. The known universe of elements spans a vast and wondrous range. Each step up the atomic number ladder introduces a new element, a new set of chemical properties, and a new chapter in the story of matter. These elements, whether forged in the hearts of stars or painstakingly crafted by human ingenuity, represent the fundamental ingredients from which everything is composed. Research shows that while the lighter elements, up to iron, are primarily formed through stellar nucleosynthesis, the gentle fusion reactions within stars, the heavier elements are often created in more dramatic cosmic events, such as supernovae or neutron star mergers. Scientists have observed that the continuous discovery and synthesis of new, heavier elements push the boundaries of our understanding of nuclear physics and the limits of matter itself. This ongoing journey of discovery reminds us that the atomic world is ever expanding, full of surprises, and endlessly inviting to our curiosity. Fact 23. Quantum entanglement suggests deep interconnectedness. Now, let us venture into a concept that truly challenges our everyday intuition, a phenomenon known as quantum entanglement. Imagine two tiny subatomic particles, perhaps two electrons, that interact in such a way that they become deeply linked, no matter how far apart they are. If you then measure a property of one entangled particle, say its small, the other entangled particle instantly and simultaneously assumes a correlated state, even if they are light years apart. It's as if they share a secret, instantaneous connection that transcends the vastness of space. Current understanding suggests that this spooky action at a distance, as Albert Einstein famously called it, is a fundamental aspect of quantum mechanics. Scientists have observed this phenomenon repeatedly in experiments, confirming that entangled particles behave as if they were part of a single unified system, regardless of their separation. While we don't fully comprehend the mechanism behind this instantaneous communication, it offers a profound, if mysterious, glimpse into the interconnectedness of the universe at its most fundamental level, hinting that reality might be far more unified than our macroscopic senses perceive. It is a quiet whisper of universal unity, inviting us to ponder the deeper fabric of existence. Fact 24. Atomic particles exhibit wave-particle duality. As we continue our journey into the quantum realm, we encounter another concept that defies easy visualization: wave-particle duality. We tend to think of particles as tiny, distinct spheres, like miniature marbles. However, at the subatomic level, entities like electrons, protons, and even entire atoms do not behave exclusively as particles. Instead, they can also exhibit properties of waves, much like ripples on a pond or sound waves travelling through the air. This means they don't always have a precise location. Rather, their existence is described by a probability wave that spreads out through space. Research shows that whether a subatomic entity behaves more like a wave or more like a particle depends on how we observe or measure it. In some experiments, an electron will appear as a localized particle, while in others it will spread out and interfere with itself like a wave. Scientists have observed that this duality is not a contradiction, but a fundamental aspect of their nature, revealing that our classical concepts of particle and wave are merely approximations of a more profound and fluid quantum reality. It is a gentle reminder that the universe, at its smallest scales, dances to a different, more enigmatic rhythm, inviting us to release our preconceived notions and embrace the quiet mystery of existence. As these profound insights settle within your mind, allow the gentle current of atomic knowledge to carry you further into a state of deep relaxation. We've explored how atoms bond, form molecules, and are organized into a grand table, revealing the elegant order of the cosmos. We have even glimpsed the mind-bending interconnectedness and dual nature of the quantum world. In our next chapter, we will continue this serene exploration, uncovering even more wonders that lie hidden within the smallest constituents of our universe, guiding you ever closer to a peaceful slumber. As we journey deeper into the atomic realm, past the mind-bending interconnections of quantum entanglement and the elegant paradox of wave-particle duality, we find ourselves at the threshold of even more profound revelations. These are not merely abstract concepts, but the very essence of the quiet order that underpins all existence, inviting us to a deeper sense of peace and wonder. Let us now gently turn our attention to the incredible spaciousness within these fundamental building blocks, a fact that often surprises and delights. Fact 31. The vast emptiness of atoms. Imagine, if you will, the nucleus of an atom, that dense material core containing protons and neutrons, as a tiny marble placed in the very centre of a football stadium. Now, picture the electrons, those fleeting energetic particles, as mere specks of dust swirling somewhere within the expansive boundaries of that stadium. This analogy, while imperfect, beautifully illustrates a fundamental truth. Atoms are almost entirely empty space. The electrons, despite their minuscule mass, define the atom's volume by their rapid probabilistic motion, creating a kind of diffuse cloud. It is this vast emptiness that forms the bulk of what we perceive as solid matter. We are, in essence, made of mostly nothing, yet we perceive ourselves and the world around us as undeniably solid. This paradox is a gentle reminder of how our senses interpret the intricate dance of subatomic particles, transforming quantum probabilities into tangible reality. Current understanding suggests that if all the empty space were removed from the atoms that make up humanity, we could all fit into a volume no larger than a sugar cube, an astonishing thought that underscores the profound nature of atomic structure. Fact 32. The electron cloud, a gentle blur of probability. Expanding on this idea of emptiness, let us consider the electron cloud, not as a fixed orbital path, but as a gentle, shimmering blur of probability. We've learned that electrons don't orbit the nucleus like planets around a sun in a neat, predictable fashion. Instead, their location at any given moment is described by a probability distribution, a mathematical wave function that tells us where an electron is most likely to be found. This creates a cloud of negative charge around the nucleus, a soft, ethereal presence rather than a hard shell. Imagine a tiny, incredibly fast firefly tracing patterns in the dark. You don't see the firefly at every point, but you see the luminous trail it leaves behind, a blur of light. Similarly, the electron cloud is the cumulative impression of an electron's rapid probabilistic movements, a constant gentle hum of energy defining the atom's outer boundary. Scientists have observed and modeled these electron probability clouds with remarkable precision, revealing the intricate, often beautiful shapes that govern how atoms interact and form bonds. Fact 33. Atoms are ancient travelers, billions of years old. Now, let us turn our gaze to the incredible longevity of atoms. Most atoms, particularly the stable isotopes we discussed earlier, are incredibly persistent. They do not simply cease to exist, they endure. The atoms that make up your very being, the chair you sit upon, the air you breathe, have been around for billions of years. They were forged in the hearts of ancient stars or during the fiery birth of the universe itself. These are not ephemeral entities, they are cosmic veterans, having witnessed the formation of galaxies, the birth of stars, and the evolution of planets. This profound persistence offers a comforting thought. The fundamental building blocks of our reality are incredibly stable, providing a timeless foundation for everything we know. Research shows that stable atoms, once formed, can continue to exist indefinitely, participating in countless transformations without losing their fundamental identity. Fact 34. The cosmic recycling of atoms, your stardust. This incredible longevity leads us to one of the most beautiful and deeply reassuring facts about atoms, the concept of cosmic recycling. Because atoms are so enduring, the atoms that constitute you and everything around you have been part of an unimaginably vast journey. They have been components of ancient stars, swirling nebulae, primordial oceans, majestic dinosaurs, and perhaps even the breath of historical figures. Every breath you take, every bite of food you consume, every cell in your body is composed of atoms that have been continuously recycled throughout the cosmos for eons. You are quite literally stardust, a transient arrangement of ancient particles that have travelled across vast stretches of time and space. This realization fosters a profound sense of interconnectedness, dissolving the illusion of separation and revealing our shared atomic heritage with all of existence. We are all participants in a grand, ongoing atomic ballet, a continuous rearrangement of the universe's most fundamental components. Fact 35. Atomic fingerprints, unlocking the secrets of distant stars. Remember how we spoke of electrons transitioning between energy levels, absorbing and emitting light to create unique spectral fingerprints? Let us now consider the magnificent implications of this phenomenon on a cosmic scale. These unique light patterns are not just a laboratory curiosity, they are the universe's universal language. When light from distant stars and galaxies reaches our telescopes, scientists can analyze its spectrum, the rainbow of colors it contains, interspersed with dark or bright lines. Each line corresponds to a specific element absorbing or emitting light at a particular wavelength. By identifying these atomic fingerprints, we can determine the chemical composition of stars, nebulae, and even the atmospheres of exoplanets billions of light years away. It is through this delicate dance of light and atoms that we have mapped the elemental makeup of the cosmos, discovering that the same atoms we find on Earth are present throughout the universe. This universal consistency provides a deep sense of order and unity, a testament to the elegant simplicity of atomic physics governing all things. Fact 36. The unseen dance of thermal energy. Even as you lie still, perhaps drifting into a peaceful slumber, the atoms that form your body and your surroundings are in constant gentle motion. This ceaseless internal jiggling is what we perceive as thermal energy. In any substance above absolute zero, atoms and molecules are vibrating, rotating and translating, colliding with each other billions of times per second. In a solid, they oscillate around fixed positions, creating a subtle internal hum. In liquids, they slide past one another, and in gases, they rush about freely. This inherent atomic motion is the very definition of warmth and heat. It is a quiet, energetic dance happening at a scale far too small for us to directly observe, yet it is fundamental to the properties of matter and the flow of energy in our world. This perpetual motion, this gentle internal dynamism, reminds us that even in stillness, there is a vibrant, unseen world of activity. Fact 37. Absolute zero and 0-point energy. The ultimate stillness that isn't. This brings us to the fascinating concept of absolute zero, the theoretical lowest possible temperature, where atoms and molecules are said to have the minimum possible thermal energy. Scientists have approached absolute zero, 0 Kelvin or 459.67 degrees in laboratories, cooling substances to incredibly frigid states. At these extreme temperatures, atomic motion slows dramatically. However, here's where quantum mechanics introduces another layer of wonder. Even at absolute zero, atoms do not become completely motionless. They still possess a tiny, irreducible amount of energy called 0-point energy. This is a consequence of quantum mechanics, specifically the Heisenberg uncertainty principle, which dictates that a particle's position and momentum cannot both be precisely known simultaneously. If an atom were perfectly still, its position and momentum would both be precisely zero, violating this principle. Therefore, even in the deepest cold imaginable, atoms continue to exhibit a subtle, quantum jiggle, a fundamental, unavoidable motion that speaks to the enduring dynamism of the universe, even at its quietest. Fact 38. Atomic clocks, the unwavering rhythm of time. From the subtle jiggle of 0-point energy, let us consider the incredible precision that can be harnessed from atomic vibrations. Atomic clocks are the most accurate timekeeping devices ever invented, defining our modern understanding of a second. These clocks work by precisely measuring the frequency of light emitted or absorbed by atoms, often cesium or rubidium, as their electrons transition between specific energy levels. Because these energy levels are so incredibly stable and consistent for a given atom, the frequency of light associated with these transitions is remarkably precise and unwavering. Imagine an atom as a perfect microscopic pendulum swinging with an absolutely consistent rhythm. Atomic clocks utilize this rhythm, allowing us to measure time with an accuracy that would lose less than 1 second over hundreds of millions of years. This extraordinary precision underpins technologies like GPS, global communication networks, and fundamental scientific research, demonstrating how the predictable nature of atomic behavior can shape our technological world. Fact 39. Bose-Einstein. Condensates, atoms behaving as one. As we delve into more exotic states of matter, prepare to be amazed by the Bose-Einstein condensate, BEC, sometimes referred to as the fifth state of matter, after solid, liquid, gas, and plasma. This incredible state occurs when a group of atoms is cooled to temperatures incredibly close to absolute zero. At these extreme lows, the individual atoms lose their distinct identities and merge into a single, collective quantum entity, behaving as if they are one giant superatom or a single matter wave. Imagine an orchestra where every musician plays exactly the same note in perfect unison, their individual sounds blending into a single resonant tone. That's akin to what happens in a Beck. This phenomenon, predicted by Albert Einstein and Satyendra Nath Bose decades before its experimental realization, offers a macroscopic glimpse into the quantum world, where the wave-like nature of matter becomes strikingly apparent. It is a peaceful, unified state of matter, a testament to the profound and sometimes counterintuitive behavior of atoms when pushed to their limits. Fact 40. Atoms, the architects of life's intricate tapestry. Finally, let us bring our journey back to ourselves, to the most astonishing creation of atomic interactions, life itself. Every cell in your body, every strand of DNA, every protein, every thought, every emotion is a complex, dynamic arrangement of atoms. From the simple hydrogen atom to the more complex carbon, oxygen, and nitrogen atoms, these fundamental building blocks, through the intricate dance of chemical bonds and intermolecular forces, come together to form the incredibly sophisticated machinery of biological systems. It is the specific arrangement and interaction of these seemingly simple particles that give rise to consciousness, sensation, and the miracle of existence. The fact that inert, non-living atoms can self-organize into the vibrant, self-replicating, and evolving forms of life is perhaps the most profound and humbling atomic truth of all. It speaks to an underlying elegance and potential within the universe's basic constituents, a silent symphony of particles orchestrating the grandest show of all. As these thoughts gently settle in your mind, we hope you feel a profound connection to the atomic world. Each fact, a tiny window into the universe's design, offers a pathway to understanding the quiet order and ceaseless wonder that permeates all things. Rest now, knowing that you are a magnificent, ancient, and ever-moving collection of stardust, intricately woven into the very fabric of existence. As we continue our serene journey, allowing the quiet order of the atomic world to settle within us, we find ourselves drawn deeper into the subtle ways these fundamental particles express their existence. We've explored their structure, their forces, their cosmic origins, and their role in the very fabric of life. Now, let us listen more closely to the whispers of atoms, to the light they emit, and to the enduring stability that underpins all that we perceive. We invite you to relax even further, letting your mind drift gently with the elegant dance of particles as we uncover more fascinating aspects of these tiny yet immensely significant building blocks of everything. Fact 41. Atoms communicate through light, each with a unique voice. Imagine a grand cosmic choir where every element sings a distinct melody. This is precisely what happens with atoms and light. When an atom absorbs energy, perhaps from heat, an electrical current, or even another photon, its electrons leap to higher energy levels, like climbing rungs on a ladder. But these higher states are fleeting, much like a moment suspended in time. Almost immediately, the electrons fall back down to their original, more stable energy levels. As they descend, they release the absorbed energy in the form of light, or more precisely photons. What makes this truly remarkable and incredibly useful to us is that each element's unique electron configuration means it can only absorb and emit light at very specific characteristic wavelengths. It's like an atomic fingerprint, a spectral signature that is utterly unique to hydrogen, distinct from helium, different from oxygen, and so on. Current understanding suggests that these precise emissions create what we call an emission spectrum, a series of bright lines on a dark background, each line corresponding to a specific colour or wavelength of light. Conversely, if white light passes through a gas of atoms, those atoms will absorb the very same wavelengths they would emit, leaving dark lines in the spectrum known as an absorption spectrum. Scientists have observed these atomic conversations for centuries, leading to the development of spectroscopy, a powerful tool that allows us to decode the composition of distant stars, identify elements in unknown substances, and even analyze the purity of materials here on Earth. This intricate dance of absorption and emission is not just a scientific curiosity, it is the universal language through which atoms reveal their identity across the vastness of space and time. It assures us that the elements we find in our own bodies are the same elements that twinkle in a faraway nebula, connecting us all through a shared, luminous heritage. Fact 42. Even in seemingly still objects, atoms are in constant, energetic motion. While we have touched upon the thermal motion of atoms, let us delve a little deeper into this ceaseless activity, for it reveals a profound vibrancy even within the most solid-seeming structures. Picture a diamond, a crystal of pure carbon. To our eyes, it appears perfectly still, unmoving, and utterly rigid. Yet, at the atomic level, the carbon atoms within that diamond are engaged in a relentless microscopic ballet. They vibrate, oscillate, and jiggle around their fixed positions in the crystal lattice. These movements are not random chaos. They are the very essence of thermal energy. This constant energetic motion is present in all matter above absolute zero, where even then, as we discussed, 0-point energy ensures a residual quantum jiggle. In solids, atoms are tightly bound but still vibrate. In liquids, they slide past one another with greater freedom. In gases, they fly about wildly, colliding and rebounding. Research shows that the amplitude and frequency of these vibrations increase with temperature, which is why objects expand when heated and contract when cooled. This internal atomic commotion is what we perceive as heat. The warmth of a gentle sunbeam on your skin, the comforting heat from a cup of tea, the very temperature of your own body, all are manifestations of this ceaseless atomic vibration. This intricate, unseen choreography of atoms reminds us that stillness is largely an illusion on the grand scale. Everything around us, and indeed within us, is a buzzing, vibrating collection of particles, constantly exchanging energy and performing their roles in the universe's grand design. It is a quiet symphony of movement, a testament to the dynamic nature of existence, offering a gentle hum of reassurance that even in apparent rest, there is an underlying profound vitality. Fact 43. Empty space is not truly empty, but a frothing sea of quantum potential. As we contemplate the vast, mostly empty space within an atom, and indeed the vastness of space between celestial bodies, it is natural to imagine it as a void. But in the realm of quantum physics, even the most profound emptiness is teeming with activity. Current understanding stemming from quantum field theory suggests that what we perceive as a vacuum is, in fact, a vibrant, frothing sea of fluctuating energy. Within this quantum foam, pairs of virtual particles, such as virtual electrons and positrons, or virtual photons, are constantly popping into existence and then almost immediately annihilating each other, disappearing back into the energy from which they emerged. These fleeting particles exist for such minuscule fractions of a second that they cannot be directly observed or measured in the traditional sense. But their transient presence has measurable effects, such as the Casimir effect, where two uncharged conductive plates placed very close together experience a small attractive force. This force arises from the subtle imbalance of virtual particles pushing on the outside of the plates compared to those between them. Scientists have observed these subtle phenomena, providing compelling evidence that the vacuum is far from inert. It is a dynamic, energetic medium, a cosmic wellspring of potential from which matter and energy can momentarily emerge. This profound insight invites us to reconsider our understanding of nothingness. It suggests that even the quietest corners of the universe are alive with an unseen, fundamental energy, a constant hum of creation and dissolution. It is a deeply peaceful thought, knowing that even in the absence of tangible things, the universe is brimming with an underlying, vibrant potential, a ceaseless dance of energy that forms the very ground of being. Fact 44, we can see and even touch individual atoms, bridging the microscopic and macroscopic. For centuries, atoms were theoretical constructs, inferred from experiments but never directly observed. The idea of seeing something so infinitesimally small seemed impossible. Yet, human ingenuity has found ways to bridge this gap, allowing us to interact with the atomic realm in astonishing detail. We cannot see atoms in the way we see a tree or a star, because they are smaller than the wavelength of visible light. However, we have developed remarkable tools that allow us to resolve their individual presence and even manipulate them. Consider the scanning tunneling microscope, STM, and the atomic force microscope, AFM. The STM operates by bringing an atomically sharp conducting tip incredibly close to a conducting surface, so close that electrons can tunnel quantum mechanically across the tiny gap. By scanning the tip across the surface and maintaining a constant tunneling current, a detailed topographic map of the surface showing individual atoms can be created. The AFM works similarly, but uses a tiny cantilever with a sharp tip that feels the surface, measuring the minute forces between the tip and the atoms. This allows us to map surfaces, revealing the precise arrangement of atoms even on non-conducting materials. Research shows that these microscopes provide images where individual atoms appear as distinct bumps or depressions, allowing us to visualize the atomic lattice of materials, study their defects, and even, in some pioneering experiments, precisely move individual atoms to spell out words or create tiny structures. This ability to see and touch the atomic world is a testament to our profound curiosity and our capacity to understand the universe at its most fundamental level. It is a wondrous realization that the abstract concepts we have explored can be rendered visible, offering a tangible connection to the invisible building blocks that compose our world, fostering a deep sense of understanding and connection. Fact 45. Isotopes undergo gentle transformation, revealing Earth's history and aiding healing. We have previously learned that isotopes are atoms of the same element with different numbers of neutrons. While many isotopes are stable, some are naturally unstable, meaning their nuclei contain an imbalance of protons and neutrons that makes them prone to decay. This process of decay is what we call radioactivity, And far from being solely a source of concern, it is a fundamental and often gentle process of transformation that has played a crucial role in shaping our planet and even assisting in our well-being. When an unstable isotope undergoes radioactive decay, it transforms into a more stable nucleus, often emitting particles like alpha or beta particles, like gamma rays in the process. This transformation occurs at a predictable rate, characterized by its half-life, the time it takes for half of a given sample of radioactive atoms to decay. Scientists have observed that these half-lives can range from fractions of a second to billions of years. For example, carbon-14, a radioactive isotope of carbon, has a half-life of about 530 years. By measuring the ratio of carbon-14 to stable carbon-12 in ancient organic materials, we can accurately determine their age, a technique known as carbon dating. This allows us to peer back into prehistory, revealing the age of ancient artifacts, fossils, and even geological formations. Beyond dating, controlled radioactivity finds profound applications in medicine. Specific radioactive isotopes, known as medical tracers, can be introduced into the body to create images of organs, detect tumours, or monitor biological processes without invasive surgery. For instance, technetium-99m is widely used in diagnostic imaging because it emits gamma rays that can be detected externally, and its short half-life ensures it clears the body quickly. This gentle transformation of atoms therefore serves as a quiet clock for the Earth's history and a silent guide for medical diagnosis, reminding us of the intricate and beneficial roles that even the most subtle atomic variations play in our world. It is a comforting thought, knowing that these tiny changes within atoms can unlock secrets of the past and contribute to the healing of the present. Fact 46. Atoms themselves are remarkably stable and enduring, the universe's ancient travellers. In our exploration, we have discussed the forces that bind atoms together and the transformations they can undergo. But let us now pause to appreciate the profound stability and resilience of the atoms themselves. Barring extreme conditions found in the hearts of stars or in powerful particle accelerators, an atom once formed is an incredibly enduring entity. The protons and neutrons in its nucleus are bound by the immensely powerful strong nuclear force, making the nucleus extraordinarily robust. The electrons, while always in motion, are more held in their quantum states by the electromagnetic force, resisting significant alteration unless energy is precisely absorbed or emitted. Consider the atoms that make up your hand, the air you breathe, or the quiet walls around you. Many of these atoms are not newly created. They are ancient travellers, billions of years old. They were forged in the Big Bang, or in the fiery hearts of long-dead stars, or in the cataclysmic explosions of supernovae. Since their creation they have persisted, merely rearranging themselves into countless forms, from stardust to planets, from oceans to living beings. Research shows that the vast majority of atoms we encounter are stable, maintaining their identity for timescales far exceeding the age of the universe itself. This enduring nature of atoms is a deeply comforting thought. It speaks to a fundamental constancy in the universe, a bedrock of existence that remains steadfast through eons of change. While galaxies collide and stars are born and die, the individual atoms continue their journey, undeterred, forming and reforming the intricate tapestry of reality. It is a profound realization that we are composed of these ancient, resilient particles, connecting us to the very beginning of time and offering a sense of deep, unwavering permanence amidst the flow of life. As these thoughts gently settle, we invite you to feel the quiet strength and enduring presence of the atomic world. The universe, in its smallest parts, whispers tales of stability, communication, and ceaseless underlying energy. Let these insights guide you further into a state of profound peace and wonder, knowing that you are intimately connected to this magnificent and ordered reality. We will continue our exploration in the moments to come, delving deeper into the subtle harmonies that govern the atomic realm. For now, allow these sats to drift through your mind like a calming current, guiding you towards tranquility. As we drift further into the quiet contemplation of atoms, we begin to perceive not just their enduring stability, but also their incredible capacity for complexity and meaning. These ancient travelers, resilient and unwavering, are not merely inert building blocks. They are the silent scribes of existence, holding within their intricate arrangements the very blueprints of life, the echoes of cosmic history, and the subtle whispers of forces that shape our reality in ways both profound and beautiful. Let us continue our gentle exploration, allowing these deep insights to cradle our minds in a serene embrace. Fact 51. Atomic memory, the blueprint of life itself. Imagine, if you will, that atoms possess a remarkable form of memory, not in the way our brains do, but in their precise arrangement and the information this arrangement conveys. The most extraordinary example of this atomic memory is found in the very essence of life, deoxyribonucleic acid, or DNA. Here, atoms of carbon, hydrogen, oxygen, nitrogen, and phosphorus are meticulously arranged into a double helix, a spiral staircase of unparalleled elegance. Each step of this staircase is a pairing of specific atomic structures, like tiny interlocking puzzle pieces. This atomic sequence acts as a universal code, a vast library of instructions for building and sustaining every living organism on Earth, from the smallest bacterium to the largest whale, and indeed to you. It is a testament to the fact that the universe can write its most complex stories using the simplest of alphabets, the atoms. Current understanding suggests that the information density within DNA is staggering. A single gram could theoretically store all the digital data in the world. This is not magic, but the precise, predictable laws of atomic bonding and arrangement, allowing for an astonishing variety of sequences within a relatively small space. Scientists have diligently worked to decode these atomic messages, revealing the intricate choreography that dictates heredity, growth, and the very functions of life. This knowledge has revolutionized medicine and biology, opening windows into the fundamental processes that govern our existence. It reminds us that even at the atomic scale, there is an inherent capacity for organization and information storage, a silent, enduring testament to the universe's creative power. We are, in a very real sense, living libraries of atomic information, passed down through countless generations. Fact 52. The quantum leap, an instantaneous dance of energy. We have spoken of electrons orbiting the nucleus, but the reality of their movement, or rather their transitions, is far more wondrous and defies our everyday intuition. When an electron moves from one energy level to another within an atom, it doesn't smoothly glide or travel through the space in between. Instead, it performs what is known as a quantum leap, an instantaneous disappearance from one state and an equally instantaneous reappearance in another. There is no intermediate journey, no gradual shift. It is an abrupt, non-local event, like a silent blink in the fabric of reality. This is because electrons can only exist at specific quantized energy levels, like steps on a ladder, and cannot hover between them. Research shows that these quantum leaps are fundamental to how atoms interact with light and energy. When an electron absorbs a specific packet of energy, a photon, it instantly jumps to a higher energy level. When it releases a photon, it instantly drops to a lower one. This is the mechanism behind the unique spectral fingerprints we discussed, the very language through which atoms communicate across the cosmos. This phenomenon, while perplexing to our classical minds, is a cornerstone of quantum mechanics, confirmed through countless experiments. It invites us to ponder the profound mystery of existence at its most fundamental level, where movement isn't always continuous, and the universe holds secrets that challenge our every expectation, unfolding in subtle, instantaneous shifts. Fact 53. Atoms as cosmic recyclers, the stardust cycle in detail. Previously, we touched upon the idea that you are stardust, and now we shall delve deeper into this profound truth, for it speaks to the very origins of the atoms that compose us and everything around us. That vast majority of elements heavier than hydrogen and helium, those crucial for life, carbon, oxygen, nitrogen, iron, were not present at the universe's beginning. They were forged in the fiery hearts of stars through a process called stellar nucleosynthesis. These stellar furnaces, burning for millions or billions of years, fused lighter atomic nuclei together under immense pressure and temperature, creating heavier and heavier elements. When these massive stars reached the end of their lives, they exploded in spectacular supernovae, scattering their newly created atomic treasures across the vast expanse of space. These cosmic fireworks enriched the interstellar medium with a diverse array of elements, forming new clouds of gas and dust. From these enriched clouds, subsequent generations of stars and planetary systems, including our own Sun and Earth, were born. Scientists have observed the spectral signatures of these elements in distant nebulae and stars, confirming this incredible cosmic recycling program. This means that the iron in your blood, the calcium in your bones, the oxygen you breathe, they were all once part of a star that lived and died billions of years ago. We are not just made of atoms, we are made of recycled stardust, intimately connected to the grand, continuous cycle of creation and recreation that spans the entire universe. Fact 54. The subtle dance of van der Waals forces. Beyond the strong, enduring bonds that form molecules, there exist far more subtle and temporary attractions between atoms and molecules, known as van der Waals forces. These forces are not about sharing or transferring electrons in a permanent way, but rather arise from fleeting synchronized fluctuations in the electron clouds of neighboring atoms. Even neutral atoms, with their balanced charges, can momentarily develop slight positive and negative poles as their electrons shift and swirl. These temporary dipoles can then induce opposite dipoles in nearby atoms, leading to a weak transient attraction. Though individually weak, the cumulative effect of countless van der Waals forces can be incredibly significant. They are crucial for many biological processes, such as the folding of proteins into their precise three-dimensional shapes which dictates their function. They also explain why geckos can stick to walls, as millions of tiny hairs on their feet create enough cumulative attraction with the surface atoms to support their weight. Research shows these forces are essential in chemistry and material science, influencing properties like boiling points and the structures of liquids and solids. This quiet, almost imperceptible dance of atomic attraction reminds us that even the gentlest whispers of force can contribute profoundly to the complexity and stability of our world, a testament to the elegant ingenuity of atomic interactions. Fact 55. Curated, the handedness of atoms and molecules. As we consider the intricate arrangements of atoms, we discover a fascinating property known as curated, or handedness. Just as your left hand is a mirror image of your right hand, but cannot be perfectly superimposed upon it. Certain molecules exist in two forms that are mirror images of each other. These are called enantiomers. While their atomic composition is identical, the spatial arrangement of their atoms is different, leading to distinct left-handed and right-handed versions. This subtle atomic asymmetry has profound implications, especially in biology. For instance, most amino acids, the building blocks of proteins, are left-handed in living organisms. Our bodies are exquisitely designed to interact with molecules of a specific handedness. Current understanding suggests that this preference for one chiral form over another is a fundamental characteristic of life on Earth, though its ultimate origin remains a fascinating mystery. In the pharmaceutical industry, chirality is critical. One handed version of a drug might be therapeutic, while its mirror image could be inactive or even harmful. Scientists have meticulously studied and synthesized chiral molecules, recognizing that the universe, even at the atomic scale, often exhibits an elegant preference for specific orientations. It invites us to appreciate the subtle, yet powerful influence of atomic geometry in shaping the very essence of life and its interactions. Fact 56. The unseen influence of the quantum vacuum. We often perceive space as empty, a void between objects. Yet at the quantum level, this empty space is anything but. It is a frothing, effervescent sea of activity, a quantum vacuum teeming with potential and fleeting existence. Here, virtual particles, pairs of particles and antiparticles, are constantly emerging into existence for an infinitesimally brief moment, only to annihilate each other and vanish back into the vacuum. This ceaseless creation and annihilation occurs so rapidly that we cannot directly observe these individual particles, yet their collective influence is real and measurable. This vibrant quantum foam contributes to what is known as zero-point energy, the irreducible minimum energy that exists even at absolute zero temperature, when all classical motion has ceased. It implies that the universe is never truly still, but always pulsating with an inherent fundamental energy. The Casimir effect provides compelling experimental evidence for this phenomenon, demonstrating that two uncharged, parallel metal plates placed very close together will experience a tiny attractive force due to the differing density of virtual particles between and outside the plates. Research shows that this inherent energy of the vacuum influences atomic properties and even the expansion of the universe. It is a profound realization that the nothingness between atoms is, in fact, a dynamic, energetic realm, a constant, silent hum underlying all existence, reminding us that reality is far richer and stranger than it often appears. Fact 57. The beauty of symmetry and pattern formation. Observe a snowflake, a crystal, or even the precise arrangement of atoms in a diamond, and you witness the inherent beauty of atomic symmetry and pattern formation. Atoms, guided by the fundamental forces we've explored, have a remarkable tendency to arrange themselves into highly ordered repeating structures. This intrinsic desire for order is driven by the minimization of energy. Atoms naturally seek the most stable and harmonious configurations possible. In a crystal, for example, atoms form a repeating lattice, a three-dimensional geometric pattern that extends throughout the material. Current understanding through crystallography allows us to precisely map these atomic arrangements, revealing the elegant internal architecture of countless substances. This atomic order dictates many of a material's properties, from the hardness of a diamond to the conductivity of a metal. The formation of these perfect repeating patterns is a silent testament to the universe's inclination towards order and beauty, even at its most fundamental level. Each atom in its precise position contributes to a larger, intricate design, a silent symphony of structure that underpins the solidity and form of our world. It offers a calming reminder that within the seeming chaos of existence, there is a deep underlying harmony and an exquisite dance of particles creating breathtaking patterns, inviting us to find peace in this profound silent order. As we continue our journey, these insights into the atomic realm deepen our appreciation for the subtle intricacies that govern all things. We begin to see atoms not just as tiny particles, but as carriers of information, participants in instantaneous quantum dances, echoes of cosmic history, and silent architects of profound beauty and order. This quiet understanding gently guides us deeper into a state of serene contemplation, preparing us for further revelations about the intricate tapestry woven by the smallest constituents of our reality. As our journey through the minuscule yet magnificent world of atoms continues, we find ourselves drifting further into the profound energies that govern their existence and, by extension, the universe itself. We have gently touched upon the predictable rhythm of radioactive decay, a cosmic clock that whispers tales of ancient Earth and the very cells within us. But within the heart of the atom there lies an even grander secret, a power that fuels stars and shapes galaxies, a power that reminds us of the incredible forces at play in the quiet order of existence. Let us now turn our gaze to the core of these tiny wonders, to the very nucleus, and discover the immense energies contained within. Fact 61. The atomic nucleus holds immense energy. Imagine, if you will, a tiny, incredibly dense core, bound together by a force so powerful it dwarfs all others we experience in our daily lives. This is the atomic nucleus, and within its confines, protons and neutrons are held in a remarkably tight embrace by the strong nuclear force. This force, as we have explored, is the universe's most potent, acting like an invisible, super sticky glue that overcomes the natural repulsion between positively charged protons. When these particles are brought together and bound, a minuscule fraction of their mass is converted into pure energy, a phenomenon described by the famous equation E=mc2. This binding energy is staggering. It is the very essence of atomic power, whether harnessed by humanity or unleashed by the cosmos. Current understanding suggests that the energy stored within the bonds of just a few atoms could power an entire city for a day, if only it could be fully and safely released. This quiet, contained power reminds us that even the smallest things hold vast, untapped potential. A comforting thought as you settle deeper into relaxation. This profound energy, locked away in the atomic heart, is not merely a theoretical concept. It is the engine of the universe. It is the process by which stars shine, illuminating the vast cosmic darkness. Fact 62. Stars are powered by nuclear fusion. Look up at the night sky or simply imagine the gentle warmth of the sun on your skin. That light, that heat, is the distant echo of atoms merging in a celestial dance. Deep within the cores of stars, under conditions of unimaginable temperature and pressure, light atomic nuclei, primarily hydrogen, are forced together to form heavier nuclei such as helium. This process is known as nuclear fusion. In each fusion event, a small amount of mass is transformed into a tremendous burst of energy, radiating outwards as light and heat. It is a continuous self-sustaining reaction, a cosmic furnace tirelessly burning for billions of years. Scientists have observed and meticulously modelled this stellar alchemy, confirming that fusion is the primary mechanism by which elements are forged and energy is released throughout the cosmos. This continuous, peaceful process of creation is happening constantly, an endless, gentle hum of atomic transformation that makes life, as we know it, possible. While fusion powers the grandest objects in the sky, another atomic process allows us to harness nuclear energy in a controlled manner here on Earth. Fact 63. Nuclear fission releases energy by splitting atoms. In contrast to fusion, where light nuclei combined and nuclear fission involves the splitting of heavy atomic nuclei into lighter ones. Imagine a large, somewhat unstable atomic nucleus, like that of uranium or plutonium. When this nucleus is struck by a neutron, it can become so unstable that it breaks apart into two or more smaller nuclei, releasing additional neutrons and a significant amount of energy in the process. These newly released neutrons can then go on to strike other heavy nuclei, initiating a chain reaction. This is the principle behind nuclear power plants, where the chain reaction is carefully controlled to generate heat, which is then converted into electricity. Research shows that fission is a highly efficient energy source, providing a substantial amount of power from a relatively small amount of fuel, without producing greenhouse gases during operation. The controlled release of such immense energy, stemming from the simple act of an atom splitting, is a testament to the elegant physics at play, offering a sense of humanity's ingenuity in understanding and interacting with the fundamental forces of the universe. These two powerful processes, fusion and fission, both hinge on a singular, profound insight into the nature of reality. Fact 64. Mass and energy are interchangeable. EEMC2. At the heart of nuclear physics lies one of the most famous equations in science, ESMC2. This elegant formula, conceived by Albert Einstein, reveals a fundamental truth about our universe. Mass and energy are not separate entities, but two different forms of the same thing. E stands for energy, M for mass, and c for the speed of light squared. Because c is an incredibly large number, C2 is astronomically huge, meaning that even a tiny amount of mass can be converted into an enormous amount of energy. Conversely, energy can also be converted into mass. This principle explains why nuclear reactions release such vast amounts of energy. A small fraction of the total mass of the interacting particles is simply transformed into pure energy. Current understanding of this equivalence has revolutionized physics, showing us that the stuff of the universe and the activity of the universe are deeply interconnected, a unity that can bring a deep sense of peace and understanding. As stars continuously fuse lighter elements into heavier ones, they eventually reach a crucial turning point, a cosmic limit that dictates their ultimate fate. Fact 65. Iron 56 is the most stable nucleus. As stars age, they become cosmic alchemists, fusing hydrogen into helium, then helium into carbon, and so on, creating progressively heavier elements. This process continues to release energy up to a certain point. That point is iron, specifically the isotope iron 56. The nucleus of iron 56 is the most stable of all atomic nuclei. This means that if you try to fuse elements heavier than iron, the process actually consumes energy rather than releasing it. And if you try to split elements lighter than iron, that also consumes energy. Iron 56 represents the energetic valley of nuclear stability. Once a massive star's core has largely converted to iron, it can no longer generate energy through fusion to counteract the immense inward pull of gravity. Scientists have observed the abundance of iron in the universe and its pivotal role in stellar evolution. understanding it as the cosmic dead end for energy-producing fusion. This atomic stability of iron is a quiet yet powerful determinant of the life and death of stars, and thus the creation of all elements heavier than itself. The inability of a star to fuse iron into heavier elements leads to one of the most spectacular and vital events in the cosmos. Fact 66. Supernovae are the universe's cosmic forges. When a massive star exhausts its nuclear fuel and its iron core can no longer support itself against gravity, it collapses inward with incredible speed, then rebounds in a catastrophic explosion known as a supernova. These are the most luminous events in the universe, briefly outshining entire galaxies. But beyond their spectacular beauty, supernovae are cosmic recycling plants and element factories. The extreme temperatures and pressures generated during the explosion create conditions ripe for rapid neutron capture, the R process, forging elements heavier than iron, including gold, silver, and uranium. Without supernovae, these precious heavy elements would not exist in the universe. Current research confirms that these explosive events scatter newly formed elements across vast distances, seeding interstellar clouds with the raw materials for new stars, planets, and even life itself. This grand cycle of stellar death and rebirth, driven by atomic processes, is a profound reminder that even in destruction, there is creation, fostering a sense of awe and interconnectedness. The distribution of elements across the universe is a direct consequence of these stellar processes, echoing the history of cosmic creation. Fact 67. The abundance of elements reflects cosmic history. If we were to take a cosmic inventory, we would find that hydrogen and helium make up about 98% of all ordinary matter in the universe. This makes perfect sense, as they were the first elements formed in the Big Bang and are the primary fuels for stars. All the other elements, from carbon and oxygen, essential for life, to silicon and iron making up planets, are comparatively rare, formed much later within the hearts of stars and dispersed by supernovae. The specific proportions of these heavier elements that we observe in stars, nebulae, and planetary systems today are like a chemical fingerprint, telling us a detailed story of the universe's evolution. Scientists have meticulously measured these cosmic abundances, confirming that the elements making up your body, the air you breathe, and the ground beneath your feet were all forged in the fiery crucible of stars long ago. This realization that we are truly made of stardust connects us intimately to the grand narrative of the cosmos, inviting a deep sense of belonging and peaceful reflection. When massive stars meet their ultimate end, some leave behind incredibly dense remnants, pushing the boundaries of atomic existence. Fact 68. Neutron stars are atoms compressed to extreme density. After a supernova, if the remaining stellar core is between about 1.4 and 3 times the mass of our Sun, gravity continues to crush it to an unimaginable degree. The immense pressure forces electrons and protons to merge, forming neutrons. The result is a neutron star, an object so dense that a teaspoonful of its material would weigh billions of tons. In a neutron star, the individual atoms, as we know them, cease to exist. Instead, the entire star becomes essentially one gigantic atomic nucleus, held together by neutron degeneracy pressure. These exotic objects are typically only about 12 miles in diameter, but contain more mass than our entire Sun. Scientists have observed these incredibly dense, rapidly spinning stellar remnants, some emitting beams of radiation that sweep across Earth like cosmic lighthouses, pulsars. The existence of neutron stars illustrates the extraordinary limits to which matter can be compressed and rearranged, a quiet testament to the incredible power of gravity and the adaptability of atomic components. For the very most massive stars, even the incredible density of a neutron star is not enough to resist the ultimate pull. Fact 9. Black holes represent the ultimate compression of matter. When the remnant core of a supernova is more than approximately 3 times the mass of our Sun, even the formidable neutron degeneracy pressure cannot withstand the relentless force of gravity. The core continues to collapse indefinitely, compressing all its matter into an infinitesimally small point called a singularity, surrounded by an event horizon. This creates a black hole, an object with such intense gravitational pull that nothing, not even light, can escape once it crosses the event horizon. Within a black hole, the very concepts of space and time, and indeed the structure of atoms, are warped and broken in ways we are still striving to fully comprehend. While we cannot directly observe black holes, their presence is inferred by their gravitational effects on surrounding matter and light. The existence of black holes invites us to ponder the very limits of physical reality and the mysteries that lie beyond our current understanding, a profound contemplation that can quiet the mind and expand the imagination. Stepping back from these cosmic extremes, let us return to the very beginning, to the faint echoes of the universe's atomic infancy. Fact 70. The cosmic microwave background is the universe's first light. Imagine looking back in time, not just millions, but billions of years, to a moment when the universe was incredibly young, hot, and dense. In this primordial soup, electrons and protons were too energetic to combine and form stable atoms. Light particles, photons, were constantly scattering off these free electrons, making the early universe opaque, like a dense fog. But then, about 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to finally combine and form the first stable, neutral hydrogen and helium atoms. This event, known as recombination, allowed photons to travel freely for the first time. This ancient light, stretched and cooled by billions of years of cosmic expansion, is what we detect today as the cosmic microwave background (CMB) radiation. It is an almost perfectly uniform glow of microwaves coming from every direction in space, representing the first light of the universe and a direct relic of the moment when atoms first formed. Scientists have precisely mapped the CMB, revealing tiny temperature fluctuations that seeded the formation of galaxies and large-scale structures. This ancient, gentle hum of the universe is a profound reminder of the atomic origins of all things, a soft whisper from the dawn of time, inviting deep serenity and connection to the vast cosmic tapestry. As we continue our journey, we will explore even more subtle, yet equally profound aspects of atoms, delving into their interactions with light and the very nature of observation. For now, let these grand concepts of cosmic energy and the universe's ancient history settle gently into your thoughts, guiding you towards a restful and contemplative state. Welcome back, dear friend, to our quiet journey through the atomic realm, a space where wonder and tranquility intertwine. As we gently drift further into the fundamental fabric of existence, we carry with us the echoes of mysteries yet unsolved, the curious handedness of molecules, the instantaneous whisper of entanglement, the profound enigma of black holes. Yet even as these grand questions beckon from the edges of our understanding, there is boundless comfort and awe to be found in the known, in the elegant, predictable dances of the atoms that compose our world. Tonight, We continue to explore the intricate ballet that shapes our reality, inviting you to simply listen, to absorb, and to let the quiet order of the universe lull you into a deeper state of peace. Let us consider once more the ceaseless motion that defines all matter. Fact 71. The temperature of atoms, a measure of their restlessness. We have spoken of atoms as being in constant motion, a vibrant, unseen dance that never truly ceases. This very motion, this kinetic energy of particles, is what we perceive as temperature. When we say something is hot, we are in essence describing a frantic, energetic jig performed by its constituent atoms and molecules. Conversely, when something is cold, these tiny dancers are moving with less vigour, a slower, more deliberate sway. Imagine a vast, invisible ballroom where every atom is a tiny dancer. In a hot room, they are whirling, colliding, bouncing off one another with great enthusiasm. In a cold room, their movements become more sedate, their collisions softer, their energy diminished. This fundamental concept underpins the very states of matter we observe all around us. Current understanding suggests that only at absolute zero, a theoretical temperature of 459.67 degrees Fahrenheit, 273.15 degrees Celsius, would all atomic motion truly cease, a stillness we have yet to perfectly achieve. This constant inherent restlessness is a universal characteristic, a vibrant energy that flows through everything, reminding us that even in apparent stillness there is always an underlying hum of activity, a gentle, perpetual motion. Fact 72. Phases of matter. The atomic dance floor changes. Building upon this idea of atomic motion, we arrive at the beautiful concept of the phases of matter: solid, liquid, gas, and plasma. These are not merely different forms of a substance, but rather different expressions of how atoms arrange themselves and interact based on their kinetic energy or temperature. In a yippee solid, atoms are like dancers holding hands, vibrating gently in fixed positions, maintaining a rigid structure. As we introduce more energy, warming the solid, these atomic dancers gain more kinetic energy. Their vibrations become more pronounced until they can no longer hold their fixed positions. They begin to slide past one another, forming a liquid, where they are still close but free to move. Add even more energy, and these atomic partners break free entirely, scattering across the entire ballroom, becoming a gas, where they move rapidly and independently, filling any available space. And beyond gas, with even more extreme energy, electrons are stripped from their atoms, creating a superheated ionized state known as plasma, the most common phase of matter in the universe, found in stars and lightning. Scientists have observed and meticulously categorized these transitions, revealing the elegant simplicity with which temperature dictates the macroscopic properties of substances, a testament to the profound influence of atomic behavior. Fact 73. Atomic fingerprints. Each element sings a unique song of light. As we gently drift through the atomic landscape, let us recall the electron's quantum leaps, its absorption and emission of photons. Each element, with its unique number of protons and its specific electron shell configuration, possesses a distinct set of permissible energy levels for its electrons. When an electron falls from a higher energy level to a lower one, it emits a photon of a precise energy, corresponding to a specific color or wavelength of light. This creates a unique spectral fingerprint, a pattern of bright lines when observed against a dark background, or dark lines when light passes through the element. Imagine each element having its own unique song, composed of light frequencies. Just as we can identify a person by their voice, scientists can identify elements, even those in distant stars and galaxies, by analysing the light they emit or absorb. This powerful technique, known as spectroscopy, allows us to understand the chemical composition of celestial bodies billions of miles away, connecting the atoms in our laboratories to the atoms that form the most distant nebulae. Research shows that these atomic fingerprints are immutable, a universal language spoken across the cosmos, revealing the shared atomic heritage of everything we see. Fact 74. The incredible longevity of atoms, cosmic travellers enduring through eons. Pause for a moment and consider the age of the atoms that make up your very being. We have touched upon this before, but it bears repeating, for its implications are truly profound. Atoms, unlike the molecules they form or the organisms they build, do not truly die or disappear under normal conditions. They are remarkably stable and enduring. The carbon atom in your breath, the oxygen atom in your blood, the hydrogen atom in the water you drink, each has likely existed since the early universe, since the first stars began their fusion dance. These are cosmic travellers, having perhaps been part of a distant supernova, a swirling nebula, a dinosaur's bone, or an ancient ocean, before finding their way into the intricate structure of your cells. They are constantly being recycled, rearranged, and repurposed, yet their fundamental identity remains. This enduring nature of atoms ensures that the building blocks of the universe are perpetually available for new formations, a grand, continuous cycle of cosmic creation and recreation. This understanding offers a deep sense of connection, reminding us that we are, quite literally, made of stardust, ancient and eternal in our most fundamental components. Fact 75. Isotopes as atomic personalities. Subtle variations, profound effects. We know that the number of protons defines an element's identity, its atomic number. But within each element, there can be subtle variations, atoms with the same number of protons but different numbers of neutrons. These are called isotopes, and they're like siblings in an atomic family, sharing the same surname, element, but possessing distinct personalities due to their varying neutron counts. While isotopes of an element behave almost identically chemically, their difference in mass can lead to profound and practical applications. For instance, carbon-12 is the common stable form of carbon, but carbon-14 with 2 extra neutrons is radioactive and decays at a known rate, allowing scientists to precisely date ancient artifacts and fossils. Similarly, specific isotopes of iodine are used in medicine to diagnose and treat thyroid conditions, while others are vital in nuclear power generation. Scientists have observed that these isotopic variations, though seemingly minor, are crucial tools for understanding Earth's climate history, tracking biological processes, and even developing new technologies. Each isotope, with its unique mass and stability, plays a distinct role in the grand atomic tapestry, adding depth and nuance to the story of matter. Fact 76. The quantum foam and zero-point energy, the living vacuum. As we delve deeper into the seemingly empty spaces of the universe, we encounter a concept that challenges our intuitive understanding of nothingness. The quantum foam, a manifestation of what is known as zero-point energy. We previously touched upon the quantum vacuum, but let us explore its profound implications further. Even in the deepest vacuum of space emerged from any matter, the quantum realm is not truly empty. Instead, it is a seething, effervescent sea of virtual particles constantly popping into and out of existence, appearing for the fleeting moments before annihilating each other. This ceaseless activity, this quantum foam, represents the lowest possible energy state of a quantum field, an inherent, irreducible energy that exists everywhere. It is a subtle, invisible ocean of potential, a constant bubbling of creation and destruction that underpins the very fabric of space-time. Current theories suggest that this zero-point energy is immense, though largely inaccessible, a constant vibrant hum that permeates the cosmos. This continuous fluctuating activity in the nothingness reminds us that reality is far more dynamic and mysterious than it often appears, a silent, powerful force that quietly shapes the universe. Fact 77. Atomic precision, the foundation of modern timekeeping and navigation. The incredible precision with which electrons transition between energy levels within an atom is not merely a theoretical curiosity, it forms the bedrock of some of our most critical modern technologies. Atomic clocks, for example, average the exquisitely consistent frequency of light emitted or absorbed during these electron quantum leaps in specific atoms such as cesium-13 or rubidium-87. Imagine an atom as a miniature, perfect pendulum swinging with an unwavering rhythm. These atomic oscillations are so stable and predictable that they define our very concept of a second, providing the most accurate and stable timekeeping known to humanity. This unparalleled precision is not just for scientific curiosity. It is the silent, invisible force enabling our interconnected world. Global Positioning Systems, GPS, rely on the picosecond accuracy of atomic clocks aboard satellites to pinpoint locations on Earth with astonishing precision. The Internet, financial markets, and global communication networks all depend on this atomic rhythm to synchronize their operations. Research shows that atomic clocks are so precise they would lose less than 1 second in hundreds of millions of years, a testament to the fundamental order and reliability embedded within the atomic structure. Fact 78. The interconnectedness of all things, a grand atomic tapestry. As our journey continues, perhaps the most profound realization to emerge from our contemplation of atoms is the profound interconnectedness of all things. From the smallest grain of sand to the most distant galaxy, from the breath you just took to the intricate thoughts forming in your mind, everything is woven from the same fundamental threads. Atoms. These tiny enduring particles governed by the same universal forces, engaged in the same quantum dances, form a single grand atomic tapestry. The hydrogen in the distant stars, the carbon in the ancient trees, the oxygen in your blood, they are all part of the same cosmic lineage, endlessly recycled and rearranged. There is no true separation, only different configurations of the same basic elements. This understanding fosters a deep sense of unity, dissolving artificial boundaries and revealing a universe that is far more integrated and harmonious than we often perceive. It is a quiet truth, a gentle whisper from the heart of matter, reminding us that we are not isolated beings, but integral threads in the magnificent, ever-unfolding fabric of existence. As the gentle current of these atomic insights carries us onward, we feel the calm embrace of understanding, a quiet knowing that permeates the very air around us. The universe in all its vastness is built upon these tiny, elegant foundations, and in their enduring order we find a deep and abiding peace. Our exploration continues, drawing us ever closer to the subtle truths that govern our reality. For now, however, let these thoughts settle softly within you, like dust motes dancing in the last rays of sunlight. Allow the wonder of the atomic world to accompany you as you drift further into comfort and rest. There is always more to discover, more quiet marvels to unveil, but for this moment, Let the universe's grand design simply cradle you. We will continue our gentle journey when you are ready to awaken to more wonders. Until then, rest peacefully, knowing you are part of an unimaginably vast and beautiful atomic story.